Hello everyone, today we're going to talk about the key management system in database encryption. This presentation will firstly introduce the general problem in database encryption, and then critically evaluate a key management system as well as the key generation process of such a system.
Database is the core of all information systems, and it's easy to be under attacks from hackers and even the internal managers. So database encryption is very important to be used to protect data, as data is the core asset of any company, and the leakage of data is likely to bring inevitable loss to the enterprise, especially for the structured data, which is widely used in the database, and the information carried by it is valuable and vulnerable to the outside. What's more, access control has also proved to be useful with regard to the security of data storage. Despite the encryption and decryption processing of data would affect the operational efficiency of database. Moving to the key considerations in database encryption, we mainly focus on two aspects. One is granularity, and another is the encryption level. For the granularity selection, columns, rows, or tables can be considered as the minimum encryption unit. The selection of granularity unit depends on the practical application. As for the encryption level, there are three levels, which are storage level, database level, and application level.
Focus on which methods can be used in the database encryption. Obviously, database encryption ensures the data security. However, the schema may have a bad influence on the efficiency of database operations. Therefore, some encryption technologies are created in order to improve the database operation efficiency. We did research on two technologies, homomorphic encryption and field subkey encryption. In order to get the sum of A and B, we cannot simply add the value in database because they become A prime and B prime after encryption. In order to solve this problem, homomorphic encryption is introduced. Given the encryption function and decryption function, a finite set M1 to Mn and two operations alpha and beta, we can do operation alpha directly on encrypted data to get a result. When we decrypt the result, we can get another result which is calculated by operation beta. Now come back to the question. We can now calculate A plus B when we find a suitable privacy homomorphism. This technology helps users do operations on sensitive data without telling their key to the database. The next technology is field subkeys encryption. The traditional method of record-oriented database encryption has a problem because the data is encrypted in units of records, so it is necessary to decrypt the entire record for each query. It will significantly increase the query overhead. Field subkeys encryption is introduced to solve it. The core idea of the subkey encryption algorithm is that perform encryption operations on records with an encryption key and perform decryption operations on fields with an decryption key. However, because the system must store two keys, this schema also increases the complexity of the key.
The key management in database is also an important task. Most databases have different security levels for different data. Therefore, based on different security levels, the data in a database have to be separated into different segments to ensure more precise control over database security. As shown in this graph, different data segments from D1 to Dn have their corresponding encryption keys from key 1 to key n. Moreover, different users consequently will have different permissions over different segments. Therefore, we have to separate users into different permission groups, and they will have their corresponding keys to access their permission data segments. However, this would allow users to have multiple segment keys, which would be a nightmare for management and storage. To address this issue, Chinese remainder theorem can be used to aggregate multiple keys into a single user key. Now we will introduce and evaluate a key management module system using such an approach. First of all, user groups will have access to the data segment. That does not necessarily mean they have full administration access to that segment. Different segments will have three types of keys: full access, write, and read. Therefore, based on this, they create a user group permission table to allow keep track of different user groups' permission types over different data segment. The key management scheme are mainly three parts: system key management, data segment key management, and user group key management. And shown in this graph, the system firstly compressed the data segment keys into segment root keys for easy storage. This key requires encryption to keep its safety. A system master key is used to encrypt it. System master key will have full access to the entire system. Therefore, it is very important to keep system master key safety. Hence, Shamir's secret sharing scheme is used to separate master keys into many subcomponents, which are distributed to different administrators. On the other hand, user group keys are generated using Chinese remainder theorem to aggregate segment keys.
Here comes three major key management, which have been mentioned similar before. System key management manages the most important key, system master key. System master key is generated when first running the CA management system automatically, and it has the highest authority among all the systems. Also, it has significant effects on creating keys for classified data and private data. Data key management is used to encrypt classified data and private data via system master key. Nowadays, the security of in-cipher-sensitive data in a database depends on the protection of the keys. Therefore, the management of keys is vital. An overall key management schema would be shown after. Finally, user key would generate according to the user class and sent to users who have already registered in CA. These slides talk about generating keys in data level. According to CISA, in 2005, there will be two approaches mentioned. The first one is just to choose random keys for each data. It is totally simple idea, and it is impossible to generate completely random keys and store all of them. It will be a terrible stuff. Then there comes a DES-centered encryption schema, and make use of classified data KJ, private data KP, and system master key K. With classified data labeled at attribute level, let AJ be an attribute identifier and K the controller master key. An attribute key to classified data is defined by AJ, encrypted by system master key via DES encryption. Users' private data elements should have a unique key. Therefore, the classification was done at data element level. It is assumed that the first field ID in every record uniquely identifies the record. For example, it is the primary key of the database, where T is timestamp included to ensure that KP is unique every time it is updated. Then comes key distributions. A copy of private data key KP is sent to the owner of the private data as a form of certificate, and the request for private data should be accompanied with its certificate for such request to be honored. Subjects can exchange their certificate with others whom they wish to allow to view their private data. However, only the private data owners can request update to private data or its certificate. So finally, in general, private data keys are refreshed more often than classified data keys, as they have greater chances to being exposed.
In conclusion, we conducted some research on the fundamental structure of key management system currently. A thorough analysis of management system and encryption function and aggregating function using Chinese remainder theory will be introduced in the final report.